What is up, everyone? It's Mr. Holtz. Today we are going to be talking about a little bit of review on atomic structure. And we're also going to be going over a brief introduction to the periodic table. So let's get started. Hopefully the review on atomic structure is review. Hopefully you remember some of this information from Science Academy. If not, there's plenty of good review out there, and I can help provide you with some extra resources if you need it. So we're going to be looking at Bohr models. And if you don't know what a Bohr model is, that's okay. But you've probably seen structures of the atom that look kind of like this, right? Similar to like the cutscene in, if you've ever seen Jimmy Neutron, right? It pulls up the atom when it's going from one transition to another. But you've probably seen some kind of picture of atoms where it has some circles in the center and then a big circle around it with some other stuff in the outside circle. Now this atom here represents an atom of helium, and we're going to be talking about Bohr models today, and what Bohr models can help us understand about atoms and their structure and how we use their structure to create this periodic table. All right. So what are atoms made of? Well, atoms make up everything in the universe, right? But we can get a little bit smaller than that. What are the parts of atoms? Hopefully, again, this is review, but atoms are composed of three major things. And those three major things are called protons, neutrons, and electrons. Now, there's some important information we should know about each one of these things, and that is as follows. All right, protons have a positive charge. They're found in the nucleus. Neutrons have no charge. They're also found in the nucleus. And electrons have a negative charge, and they're found outside the nucleus. Now, what's the nucleus? Because we also have the nucleus of a cell, right? But we're talking way smaller than that. Right now, the nucleus represents anything in the center of the atom, right? So all the protons and the neutrons we have are clumped together in the center of the atom, and the electrons are found in energy levels somewhere outside the nucleus. Now, depending on the atom, we'll find electrons in different energy levels, but we'll talk about that in a little bit, all right? So this is a generic atom picture that represents the information that we can find on the periodic table. Now, when you look at the periodic table, you'll just find a bunch of boxes, right? And each of those boxes represents an individual atom, like this example I have up here for hydrogen. Now, hydrogen is the first element in the periodic table, and it has some important information in this box. So let's go through that. Generally, you'll find a whole number at the top. Sometimes it's in one of the corners. Sometimes it's centered in the middle. You'll find an element symbol, the name for the element below that, and then a number down at the bottom that's usually not a whole number. Now, what are these numbers and what do these symbols mean? Well, the symbol is the element symbol, or it's just an abbreviation to represent what that element is, right? Hydrogen is element 1. It has an abbreviation of the letter H, just because chemists are lazy and they don't want to have to write out hydrogen all the time. Now, the number at the top refers to the atomic number. So what is the atomic number? Well, the atomic number is really just how many protons. So it's our number of protons. Now, why is it the number of protons? Well, protons determine the character, or protons determine the identity of that atom. All right. So here I have helium. If you look really close, you'll find that I have 2 protons here in the center. So if our number of protons is the atomic number, in this case, since we're talking about helium, the atomic number would be 2, because there's only 2 protons in the nucleus. So here, our atomic number is 2. Now, why is that important? Well, just like on cars, for those of you that have a car, or if you've ever bought an iPhone or a laptop, like a MacBook, Apple puts specific identification numbers for each iPhone. Car companies put VIN numbers, or vehicle identification numbers, for each car they make, right? That number is specific to an individual car. No 2 cars have the same VIN number. Just like on the periodic table, no two elements have the same atomic number, because it's based on how many protons they have. Now, for example, our helium here has 2 protons in the nucleus. So if we took one of them out, if we just got rid of one of these protons, obviously there'd only be 1 left. But because the atomic number, or the number of protons, determines the identity of an atom, once I take away one of these protons and we're only left with 1, this is no longer helium. This atom now becomes hydrogen because it only has 1 proton. So we have effectively changed its atomic number and changed its identity, okay? Same thing would happen if we added a proton. It would no longer be helium. It would be the next element up in the periodic table, which is actually lithium, all right? So the atomic number determines what type of atom or what the identity of that atom is, and it's based solely on how many protons we have, all right? Now the next number on here is the atomic mass. Now, the atomic mass is slightly different than the atomic number, but it does include how many protons we have. All right. So, for example, again, here's our helium atom. If you look at the periodic table, you'll find that the atomic mass for helium is about 4. So why is it 4? Well, if you look at the center or the nucleus of this atom, you'll find that we have 2 protons and 2 neutrons. So this is actually where all of the information for our atomic mass is coming from. Now you might be asking, well, there's 2 electrons here. How do those electrons interact with the, or increase or deal with the atomic mass? The electrons actually are not involved in the atomic mass, and the reason for that is because once you get down to the subatomic scale, you'll find that protons and neutrons are about the same size. So everything in the nucleus is about equal in size or mass. Now, electrons are really, really tiny. Even compared to protons and neutrons, they're super, super small. So you could have an element with 2 electrons. You can have an element with 200 electrons. Now, we haven't discovered element 200, but hypothetically, you could have an element with 200 electrons, and they're so small that even 200 electrons doesn't influence the atomic mass, right? That atom will have about the same mass because the electrons are so, so small. It doesn't really matter how many of them you add. It doesn't increase the mass at all because they're just so, so tiny compared to the protons and the neutrons. So the atomic mass is really the protons plus our neutrons. All right. Now, because they're protons plus neutrons, those are really the heavy part of the that makes up the atom. And because we have 2 protons here and 2 neutrons here, obviously 2 plus 2 is 4. So that's where our atomic mass comes from. Now, as another example, you'll find that the atomic mass of hydrogen is just over 1. Now, later on, we'll talk about why these are not always whole numbers. But as you can see, it's about 1 for our purposes right now, which is equal to the atomic number. As we know, the atomic number for hydrogen is 1 because it has 1 proton in the nucleus. And since its atomic mass is also about 1, then we know there's no neutrons in the nucleus, right? If there was a neutron in the nucleus, then our 1 from the proton plus any neutrons that were there would obviously be more than 1. So hydrogen, if you didn't already know, is just a proton and an electron, right? Still has to balance out the number of positives and negatives, but it doesn't have any neutrons, and we can figure that out because these 2 numbers are almost exactly the same, all right? All right, let's get into the periodic table and kind of how it's structured and how we came up with it, and then we'll talk a little bit more about Bohr models in just a minute. So here's a generic looking periodic table. Obviously, I haven't filled it in with all of the elements, but I've labeled each of the sections. Let me see if I can rotate this here a little bit. All right. So let's just go over what each of the sections are. Now, the periodic table is structured in kind of 2 different ways. It's structured both across from left to right and up and down, right, in these columns. So the columns are actually referred to as groups. So this is group 1, group 2, etc. as we move down over to group 8 or group 18. It depends on what the periodic table is that you're looking at, because sometimes they count these groups and sometimes they don't. So the groups are the up and down columns as we move across, but obviously this is not called the group table, right? This is called the periodic table. So why is it called the periodic table? Well, not only do we structure it based on the categories of up and down and how those elements are related to each other, we also organize them from left to right. Now, these rows are actually referred to as periods from left to right on the periodic table. So the reason it's called the periodic table is because it's periodic, right? And these rows from left to right are referred to as periods. But let's go through the different groups or different sections of the periodic table just so we have a good understanding of what categories of atoms are centered where. So group 1 is referred to as our alkali metals. You don't really need to know what that means, but that's their term. Just know that they're metals, and we'll talk about their characteristics later on this year. Group 2 is very similar in their characteristics, but a little bit different, and again, we'll talk about that later on. These are referred to as our alkaline earth metals. Again, another group of metals. So they have similar characteristics. Now, this big section in the middle right here, hopefully you can read it, is referred to as our transition metals. Now, transition metals are all the typical metals you'll think of, like platinum and gold and nickel and silver and copper, all that kind of stuff. So that's where our transition metals are found. Now, these have some pretty interesting characteristics that we'll get to later this year, but these can get pretty complicated in higher level chemistry. Now, the group that's kind of pulled down and sectioned out from the rest of the periodic table is referred to as our rare earth metals. Now, the rare earth metals obviously are earth metals. They're metals that are found on Earth, but they're found on Earth rarely, right? Things like plutonium, I think technetium is a rare earth metal. So some stuff that's found in really small quantities. Sometimes they're used in tech parts and stuff like that, but they really fit in right where this little black line fits in. So I would just, if I were you and you're confused about this, try and follow them based on their atomic number and see if you can figure out how it works. Because this section really fits in right here. So if you tried to draw out the periodic table correctly, like 100% correctly, it would really push all the transition metals over and make it like twice as long. But that doesn't really fit on mugs and t-shirts and pieces of paper and posters very well. So they've sectioned it out so that this can be a little more structured and organized in terms of printing it out and using it as a format. So again, these are another group of metals. So what you'll find is a large majority of the left side of the periodic table is all kinds of metals, and that'll become very important later on this year. Now, the next group we're going to talk about is metalloids. Metalloids, sometimes you'll hear them referred as semi-metals. This is kind of a group of some funky atoms. Now, they're kind of funky because depending on either what atom they are or what circumstances they're used in, sometimes these elements have metallic characteristics and they act similarly to the other metals I've just introduced, and sometimes they don't, all right? Things like lead and gallium are in these metalloids, and if you don't know about gallium, it's awesome. Mr. Johnson has a sweet sample of it, so maybe I'll see if I can borrow that later this year. But I'd look up gallium, all right? Gallium is a metal that has a melting point that's higher than room temperature. So at room temperature, it's a solid, but it's lower than your body temperature. Your body temperature is a little under 100 degrees Fahrenheit, but we'll be using Celsius most of the time. But gallium, if you hold it in your hand, the melting temperature of gallium is actually lower than your body temperature, so the metal will start to melt in your hand. Now, I can't really list any other metals that melt in your hand, so because it shows some metallic characteristics and some non-metallic characteristics, that's a metalloid, all right, or a semi-metal. Now, our non-metals are things like oxygen, nitrogen, carbon, most of the stuff that's found in organic compounds that make up living things, sulfur, some stuff like that. So obviously, oxygen, nitrogen, almost everything that's found in the atmosphere, oxygen gas, nitrogen gas, clearly those are not metals, right? They don't have metallic characteristics. Carbon is another good example. We use carbon to make graphite. We also use carbon to make diamonds. Neither of those things are metals, even though diamond's really strong, but they don't show metallic characteristics. So this section is referred to as our non-metals. Now, the groups over here that I'm going to talk about in a second are also non-metals, but they have their own names. And they have their own names, again, because their characteristics are really similar, which is why we organize the periodic table the way that we do. So the next group is group 7 or group 17, again, depending on which group you're looking at, or which periodic table you're looking at. These are our halogens. So these are things like fluorine, chlorine, bromine, iodine, and we'll talk about their importance later on this year as well. The next group and the last group we need to talk about is the noble gases. Now, noble gases are things like helium and neon. Again, they're different kinds of gas, xenon. But one thing that we'll learn about noble gases is that they're super unreactive. They're noble, they're hoity-toity. They don't like to interact with the other lower elements, all right? So they don't really interact with stuff, right? Helium is a great example. Helium balloons, they can pop, but they don't really explode, right? Helium's not an interactive element. It doesn't react to stimuli or other circumstances. So we'll talk about why that is in a minute. But this is a general outline of the periodic table. And we'll talk about these characteristics and aspects later on this year. So let's go back to the Bohr model a little bit. And there's one concept with the Bohr model. Here we go. One concept with the Bohr model I want to make sure we cover. And that is hopefully something you've already heard of, but that is called the Octet Rule. Now, what is the Octet Rule? Well, the Octet Rule states that atoms like to form bonds so that they end up with a total of 8 valence electrons. Well, what's a valence electron? Well, going back to our example of helium, these two electrons, this electron here and this electron here, are called valence electrons. So what does that actually mean? Valence really means electrons on the outermost ring or the outermost energy level of that atom. So obviously, this helium atom only has one ring of electrons on it, but if I added another ring here, and we'll talk about why this happens in just a second, but if I added another ring here, any electrons you would find on this outer ring would be referred to as our valence electrons. So they're just the electrons on the outside most energy level. And we'll look at that again in just a second, all right? So basically, atoms really like to have or end up with a total of 8 electrons in their outermost ring. So why is it 8? Why isn't it another number? Now, there are exceptions to this, but let's talk about why that number is 8. Why is it not something else? So here's a generic Bohr model. Now, I have the NuC in the center to represent the nucleus, right? This is where all of our protons and neutrons would be. But since right now we're concerned about valence electrons and how we organize them, the stuff in the nucleus isn't that important to us. So we'll just leave that NuC there to represent that for us. Now, I know this periodic table is kind of hard for you guys to see, but I'll be pointing and referencing each element as we go along. But it might be helpful to either have one next to you or pull another one up in a tab on your computer. So element number 1 is hydrogen. Now, again, we need to balance the number of protons and electrons. So for every atom we go up in atomic number, meaning like from element 1 to element 2, we have to account for that extra electron, all right? So element 1, hydrogen, has 1 proton because we know its atomic number is 1. And if it has 1 proton with a positive charge and we want to keep that atom neutral, we also need 1 electron to keep the positives and negatives the same. So here's my 1 electron that is in hydrogen, all right? Now, if we move over to element number 2, it's helium. And again, because we added another number, element to element number 2, now we need to add another electron to balance out that positive charge of the extra proton in the nucleus. So element 2, helium, has 2 electrons. So here's electron number 2. All right. Now something interesting happens when you move to the next one. Obviously, after helium, there's nothing right here, right? It's just blank. It's my whiteboard. That's because element number 3 is not in the first row, right? It's not in the first period on the periodic table. It's in the second period. So element number 3, lithium, is actually in the second row down here, all right? Now, we compare Bohr models to the periodic table just like that, all right? Lithium is in the second row, but if we added another electron to it, we still need to account for that because it's element number 3. It has 3 protons in the nucleus. But as you can see, just like the element lithium doesn't fit here, it moves down to the next row. In our first ring, if we tried to add an electron, and obviously there's no spot here because I drew it like that, but there's clearly no spot here for that electron. So just like lithium jumps down to the next row and then starts after that, the next electron for lithium would also jump to the next energy level and then continue adding from there, all right? So here is electron number 3. That represents the electron that we added for element lithium, right? Lithium now has 1, 2, 3 electrons, and it would have 3 protons in the nucleus. Now, the next element after that is beryllium, element 4. So again, I'm going to add 1 more electron to represent that element, all right? Now, just as a refresher, This is beryllium. Beryllium has 4 electrons because it's element 4. Notice that 2 of them are in the first energy level and 2 of them are in the outer energy level, which means, this one's kind of light, which means these 2 electrons are referred to as the valence electrons, okay? These are the electrons in the outermost energy level. So even though beryllium has 4 electrons in total, only 2 of them are in the outermost energy level, meaning it has 2 valence electrons, all right? Now the next element, element number 5, is boron. I'll add another electron for boron. The next element after that is carbon. So I'll add another electron for carbon. After that, we have nitrogen. So another electron for nitrogen. Another electron for oxygen, which is the next element. So if we look at oxygen, oxygen's element 8, and we have 1, 2, 3, 4, 5, 6, 7, 8 electrons. But keep in mind, only 1, 2, 3, 4, 5, 6 of them are valence electrons, all right? Moving on, after oxygen, we have fluorine. Fluorine will add 1 more electron. And after fluorine, we have neon. Here we go with our electron for neon, all right? Now, going back to the octet rule, how many electrons or how many valence electrons do atoms like to have? They like to end up with a total of 8 valence electrons. Now, why is it 8 valence electrons? Well, like I said, the noble gases are super, super hoity-toity, right? They're stable. They don't need help from anybody. They like to hang out and not really react at all right? Now, neon is a great example of a noble gas. Neon is in all those lights in restaurants and businesses and bars that tell you whether they're open or not. But neon has a total of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 electrons, which is good because it's element 10. But how many of these are valence? Well, we can't count the 2 in the first ring because they're not in the outermost energy level. So the 1, 2, 3, 4, 5, 6, 7, 8 electrons in the second ring constitute all of the valence electrons for neon. Now, because elements like to fill their valence shell, neon has already done that, meaning it already has 8 electrons here. Now, because it has 8 electrons, and we know that atoms like to end up with a total of 8 valence electrons, neon is already there. So neon won't really be reacting with any other elements or any other atoms because it doesn't need any more valence electrons. It's already filled this ring, right? So this is why noble gases don't react with other elements. They've already filled their total number of valence electrons that they need, so they don't need to borrow any from anybody else, or they don't need to steal any from another atom. All right, let's look at one more example. After neon, again, there's nothing here. The next element, element 11, which is sodium, is down again to the next period. All right, so just like last time, I'm going to continue to add electrons. So here's my 1 electron for sodium. All right, now we have a total of 11 electrons. How many of them are valence? Well, now we've moved to the third ring, right? Our third energy level, or orbital, if you want to call it an orbital. There's plenty of terms you can use for it. But only 1 electron is in this ring. So sodium is the first element in group or in period 3, and it only has 1 valence electron. Okay. After sodium, we have magnesium. So I'll add another one. After magnesium, we jump over to aluminum, element 13. After aluminum, we have silicon, and then phosphorus, and then sulfur, and then chlorine. And after chlorine, element 18, another noble gas, we have argon. So here's my electron for argon. Now, again, noble gases don't like to interact with other stuff because they have already met their valence shell requirement, right? They've already met the octet rule. Argon has 1, 2, 3, 4, 5, 6, 7, 8 valence electrons in its outermost shell. Now that they're all filled, it doesn't need to borrow or steal any. So argon won't be reacting with any other atoms. Now, if you were to continue this after argon, element 19 is potassium, all right? It's in the 4th period on the periodic table. But if you start at period 4 and you go all the way across, you'll find that now we're encompassing the transition metals, right? That middle section right here, all these metals in the middle. Now, because we're encompassing these, if we were to draw another circle out here, obviously that ring would be huge, especially compared to our first ring. So if you wanted to continue with the trend for the Bohr model, the next ring would actually fit, and I'm going to start with potassium and go all the way across over to krypton, which is element 36. Now, if you can do the math using atomic numbers, great. It's 36 minus 18 because it's the number we end with minus the number we start with. And that will tell us how many total atoms there are here, but I'm just going to count them. 1, starting with potassium, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Krypton is the 18th element in this period. So if you were to draw another ring out here to represent that energy level in a Bohr model, just like we're looking at right here, you'd actually have to fit 18 spots for electrons. Now, clearly, fitting 18 spots for electrons here doesn't match up with the octet rule. Because if now those elements are trying to fill 18 spots for electrons, clearly 18 is more than 8. Now, yes, that is true. However, when we're talking about the octet rule, most of the atoms that we're really concerned with are these nonmetals over here, because once we start talking about atoms and how they interact and how they form bonds and how we create molecules out of these individual atoms, and we use the octet rule to create those drawings and make things like Lewis dot structures and figuring out how different compounds are formed, we're really going to be using the elements that are in this second row and the third row, all right? So both of these rows have a valence shell of 8 electrons. So the octet rule isn't so much a requirement for every atom on the periodic table, but it's a rule of thumb that tries to represent how most of the atoms we run into, like carbon, nitrogen, oxygen, sulfur, phosphorus, silicon, all the common atoms that we'll be using, those all do follow the octet rule because they have very similar valence shells, right? Once we get down to things like iron and copper in the transition metals, we'll find that they act slightly differently, but that's something we'll tackle later this year, all right? So hopefully that was a good review on atomic structure and talking about Bohr models and valence electrons and why the periodic table is kind of strangely shaped the way that it is. And we went over the groups of the periodic table, and we'll apply the different groups and their characteristics to concepts that we'll talk about later this year. So hopefully that was helpful. Again, if you have any questions, feel free to send me an email or type something up and post it on our Google Classroom.